एकमात्र ओडिया रूपे सर्वभारतीय INMA पुरस्कार लाभ करथिले। प्रोफेसर मिश्र मध्य जने प्रथम ओडिया भावे जातीय विज्ञान एकाडेमी जाको में NASC नाम रे जानो सेठी फेलो रूपे मनोनीत होइथिले। प्रोफेसर मिश्र टेक्स्ट बुक ब्यूरो रो मुद्रण दायित्व नेथिले। निर्भीक एवं सत्यनिष्ठ प्रोफेसर मिश्र को गर्व अहमिका स्पर्श मध्य करनथिला। जातस्य हि ध्रुव मृत्यु ध्रुवं जन्म मृतस्य च। प्रोफेसर मिश्र स्कूटर दुर्घटना जोगु श्री गुंडीचा यात्रा दिन स्वर्गारोहण करथिले। तांको मृत्यु जोगु ओडिशा जन प्रतिभाशाली गणित अध्यापक को हराइथिला। धन्यवाद।
Thank you, Sangram. Now we just sort. Thank you, Sangram. This is the short discussion about the Professor Shankar, Professor Mishra. Now today we have with us Professor Trilochan sir, Department Ocean Engineering and Naval Architecture, IIT Kharagpur. Sir will deliver a talk in memory of Professor Shankar, Professor Mishra about the blocking dynamic of flexible gravity waves, a brief overview. So regarding Professor Trilochan sir, I request my student Swati to give a short introduction of Professor Sahoo. Over to Swati.
Good morning, everyone. I am very delighted for having the opportunity to introduce Professor Trilochan Sahoo. He is currently working as a professor in the Department of Ocean Engineering and Naval Architecture, Indian Institute of Technology, Kharagpur. His primary research focus is on developing mathematical tools for wave structure interaction problems arising. His interests include hydroelasticity of floating and submerged structures, Bragg scattering of surface waves, and so on. He is serving as Associate Editor of OEME and is a member of editorial boards of AOR and JEME. He started his research career in Indian Institute of Science, Bengaluru in 1991 as Junior Research Fellow. In 1993, he became Senior Research Fellow in IISc. He further continued as a postdoctoral fellow in the University of Hong Kong from 1997 to 2000 for 3 years under Professor Ellen T. Schwang. He then started his teaching career as Assistant Professor in Department of Ocean Engineering and Naval Architecture, IIT Kharagpur. He has published about 180 and more papers in different contexts of his area of interest. We feel extremely privileged to have him among us, delivering the Professor Shankar Prasad Mishra Memorial Lecture. Now I will ask Professor Trilochan Sahoo to take over the proceedings. Sir, please.
Thank you for your nice introduction. It's a proud privilege for me to deliver the opening talk in the memory of Professor Shankar Prasad Mishra. Professor Shankar Prasad Mishra was at IIT Kharagpur in his 1960s. It is almost after a gap of 50 years. One of his grand students is standing before you to deliver the memorial talk. In this occasion, I pay my tribute to Professor Mishra before I start my lecture. It's an honor for me to deliver the opening memorial talk. In OMS, I thank the organizers of OMS for giving me this opportunity to deliver this opening talk. My special thanks goes to Professor Jaswant Janna, the Director IMA, and his team, especially Dr. Sudhakar Sahoo, who have arranged all the logistics in organizing this event, and also having several communication with all the speakers and including myself. They have taken a lot of pain in organizing this. I am very much delighted further to note that today's session, morning session, we are meeting three batchmates of mine, myself, Dr. Professor Jaswant Jaina, the director IMA, and Professor Rajan Kumar Sinha, who is also one of the speaker of the morning session. In fact, we all are 1989 batch MSc from Utkal University, and I have the privilege to meet again after a long gap. Three of us together, individually we have met, but meeting together is a very rare occasion. So, thank you for giving us this opportunity to again meet here at this forum. So with this introduction, and I pay my regards to all my teachers, Professor Padi, Professor Das, Professor Patnaik, and other teachers in the university, and also most of the teachers, since it is OMS, my college teachers are there from BJP College, Basic Science College, where I have did my undergraduate studies. With this, I again thanks to the organizers for giving me this chance to deliver this talk. So I'll share my screen now. Full screen. Is my screen visible?
Yes, sir.
Yes,
Okay.
it is visible.
Okay, so the title of my talk has been told that it's blocking dynamics of flexural gravity waves, a brief overview. So what I'm going to talk, the outlines of my presentation will be, first of all, I'll talk today what are the global challenges for the 21st century, then hydroelectricity and introduction, areas of application of hydroelectricity, some of the basic features, basically associated mathematical problems, and how we model the problems of hydroelectricity. And then I will give some review of some of the expansion formulae, and then I talk about the blocking dynamics of flexural gravity waves, which is just an overview, and it's one of the very recent topic of interest. So then with this, I'll conclude my talk with a future scope. I'll try to be within time. So some of the global challenges. Today we have the biggest challenge is Corona. Anyway, this is today's challenge, but then but some of the major engineering challenges for the 21st century are because of the need for space for infrastructure, air pollution, technological changes and affluent living style, spread of vector-borne diseases such as H5N1, water pollution, both drinking and groundwater. And in fact, I will include to that the coastal water. Global warming is one of the biggest challenges, which leads to storm surge and sea level rise, energy need, scarcity of food, and then population growth. So now coming back to the subject of hydroelectricity. What is hydroelectricity? It is the branch of fluid structure interaction which deals with the mutual interaction between the hydrodynamic and elastic forces. Especially, it is the interaction of ocean waves with the structures. You can see on the right side there is a large floating structure. When such a structure of around 5 to 7 kilometer length is floating on the water surface, and it is almost considered, even if it's considered as a flexible body, and the body, when it interacts with the ocean waves, that is a gravity wave. In structure, there is a wave that what we call the flexural wave, and it interacts with the gravity waves that is propagating in the ocean surface. That mutual interaction gives us the flexural gravity waves. So now, why this study is so important? You see that there is a couple of floating bridges on the left side, and collapsing of these bridges due to wave action, and also the breaking of a hull girder at a mid-ship coast due to lack of longitudinal strength, and the structure is also in water. So the failure analysis of this structure is one of the motivation why this subject is more important today. hydroelectricity for ocean space utilization. This subject has taken momentum in this almost last 30 years because of the need of space for various activities such as airport space, floating bridges, breakwaters, piers and docks, military base, industrial space, emergency bases, storage facilities, mobile structures, and so on. Now, coming back to another area of hydroelectricity is polar engineering. A large part of if you look at in the polar region, particularly in the McMurdo Sound in Antarctica, since 1957-58, the ice-covered sea surface is being used as an airport. And in fact, it's a 6-meter thick ice, which is enough for an aircraft to land and take off. And then because of global warming and various issues, often cracks are occurring in the ice sheet. And so it is very important to understand this.
Excuse me.
Yes, please.
How your slides are not changing?
Changing? But
Yeah.
I am changing.
Yeah. It is not in the display mode. Sorry.
Yeah, okay, let me see.
Yeah, it is. Can you make it full screen?
No, I have made it full screen. Which slide is showing?
You are in two computer. Is it in one computer you are, or in a two computer? That's
No, I'm in single. I'm in a single
it was
computer.
not changing. Sorry.
Is it? Okay, let me try again. Just
Please do again. Sorry.
okay. Is it visible?
Yeah, it's coming. It's coming correctly.
Okay, so now coming back to the hydroelectricity polar engineering. In polar engineering, as I mentioned, that the sea surface is being used for railroad transport as well as for landing up and take up of aircrafts. So this is also another, and in the context of global warming, the subject is again taking momentum. So another area of hydroelectricity is in mariculture. Basically, it is a fish farming in the ocean water in the deep sea. It's not catching fish from the open sea. It's fish farming in the open sea. And then another area is some of the challenges for the 21st century, what we call them as the mega projects for very large floating structure. And these are some of the engineering challenges. That is the proposed floating airport for San Diego, which is around $20 billion project. Similarly, we have seen that conceptual design of a floating island city of overcrowded countries. It is basically we are looking at 50,000 population, a city of 50,000 population with all facility. It will be on a floating platform. And this is countries like Netherlands and Dubai. They are more interested in this kind of floating city. And another challenge to the Heathrow International Airport is that the crowd and population, the crowd in the Heathrow International Airport, to meet that challenge, they're planning to have another airport that is a floating airport in the Thames estuary, London. It is almost 47.3 billion UK pound. So like this, there are several major challenges. Once one of the issues is resolved, then perhaps all these issues will be resolved. So this brief background about hydroelectricity and some of its application and its motivation, I'll just go for a mathematical modeling of this. And in the modeling, we assume the fluid as invisible and incompressible. And for simplicity, for the calm water zone, we always consider the flow is rotational and simple harmonic in special cases for time. For basically frequency domain analysis, we go for simple harmonic motion. On the other hand, for time domain analysis, unsteady problem also will deal with later. But today's talk will be on simple harmonic when the motion is simple harmonic. So here we assume that wavelengths are very small compared to the horizontal size of the structure. Fluid is assumed to be three-dimensional, and Euler Bernoulli beam equation or the Timoshenko plate equation is used for structural analysis, and both a single and two-layer fluids will be considered in this problem. So here, I'll just say that briefly, what is the basic water wave theory just in one slide. We'll see that governing equation is Laplace equation, whereas if the seabed is uniform, then we have a phi z is 0 at the bottom. On the other hand, on the free surface, there are two conditions. One we call the kinematic condition, and another is the dynamic condition. See here, the kinematic condition is again you can see this is a nonlinear equation. That itself is a condition on the free surface at z is equal to minus eta. And another condition comes from the dynamic condition. That is again, so these two conditions are satisfied simultaneously on the free surface in the case of water. So, but then we are solving Laplace equation. On school, in our college, university days, we all know that when you solve a Laplace equation, you are familiar with the Neumann, Dirichlet, and Rubinstein boundary condition. But here the conditions are very complex and non-linear in nature. So, this is in case of basic water wave theory. But on the other hand, when I say that large floating structure is there, we always take the pressure on the surface, pressure exerted on the flexible plate. I've given a very complex expression where kappa is again eta xx by 1 plus eta x square. It's a nonlinear expression. And you have a kappa q term also. And then on the other hand, if I say that if I go for Euler Bernoulli, the simplest form, the Euler Bernoulli equation, if I go, then, sorry. If I go back to the Euler Bernoulli equation, I think I have, yeah, sorry. So if I go back to the linearized dynamic boundary condition, then this becomes the second equation here. It is a linear one. On the other hand, for capillary gravity waves, P is equal to minus T kappa, and that is the pressure that is on the free surface in different cases. But if I couple this plate covered boundary condition, the pressure on the free surface with the other two conditions on the dynamic and kinematic condition on the water surface, that gives me a very complex equation. That is basically a complex condition on the free surface. See, governing equation is a Laplace equation, whereas the free surface condition, one is the kinematic condition, whereas the dynamic condition is very complex. And that makes the problem more complicated, very, very complex problem in general. Now, this is in case of the finite water depth. But in the case of long wave theory, in the case of long wave, if I assume the flow is dominant along the horizontal direction, vertical velocity component is negligible, then in that case, the equation of motion and equation of motion gives rise to this is the equation of continuity that will reduce to this one, and then the equation of motion. This is linear again. And if epsilon is 0 here I took, then this will be epsilon is 1 leads to Wozinski theory, whereas epsilon is 0 gives the Aries wave theory. And again with this, this is a very complex problem, so I'll just go to the corresponding linear problem. In the case of the linear problem, we solve, I'm not spending much time. Here the kinematic condition is simplified, the dynamic condition is simplified. So in case of water, the free surface condition becomes very simple. And then we have so it is easy to handle. On the other hand, in case of under shallow water approximation, you will see that this is the kind of wave equation it is satisfied. And so that is what. Now, coming back to the basic structure equation on the linear theory, this becomes much simpler with thin plate theory. And then we have the membrane. If E is 0, then it reduced to the theory of the membrane. And then additional structural condition I just impose because why I'm introducing to this boundary condition a kind of equation that how complex equations we are dealing with in solving a problem associated just with the Laplace equation. And the Euler Bernoulli beam equation becomes this. This is the, on the other hand, if I say that the structure is on a basic foundation, I have earlier taken that it is bottom is 0, that velocity is 0 at the bottom, uniform bed, assuming it's a rigid bed. But if the bottom is a muddy bed or a sandy bed, sometimes we model it as a viscoelastic bed. And in case of a viscoelastic bed, my condition is more complex, and I have given it here. So anyway, so this is, if you go on changing the things will be more and more complicated. Now coming back to the governing equation and coupled boundary condition, in fact, this is the structure of the equation, governing equation, Laplace equation. You have the kinematic condition, and you have, in case of two thick plate and thin plate, I have the conditions here. So with this, then I'll go back from a thin plate to thick plate because these are some of the physical conditions. And with this, I'll again, in case of a long wave, my conditions will be reduced to, I'll be solving the wave equation. In case of long wave, the wave equation reduces to, for the water wave, it will be second order, whereas in the plate covered surface, it becomes a sixth order equation. And basically, the wave equation becomes sixth order. Normally, we have studied up to second order. The wave equation is second order here. So anyway, so shallow water, you can see here, plate covered region. This is the open water region, second order. plate covered region, the shallow water equation is long wave equation is 6th order, whereas in the case of a 2-layer fluid, this if it is open water, it's 4th order, whereas in case of in 2-layer fluid with a plate covered surface, it's 8th order. All you will see that these are all generalization of the wave equation, and that happens in case of. Now with this brief introduction, I'll now summarize some of the results which we have over the years people have done basically. So if you look at the structure of the mathematical problem, we are dealing with a governing equation is Laplace equation, and the free surface on the surface y is equal to 0, I have a differential equation. I put it in the operator form. L is a n plus 1th order differential equation, and m, the operator m, is again a 2m0, m is equal to, this is m0 times, it is a 2n types. So 2n plus 1 order differential equation which is satisfied on the free surface, whereas the governing equation is a Laplace equation. And depending on the, if I say the seabed is rigid or it is infinite depth, you have the simplest one, but with the introduction of a viscoelastic bed, or the condition will be again changing and it will be more complex. So basically, if you look at, I have a second order wave equation I'm dealing with, second order Laplace equation, whereas my boundary condition is 2n plus 1/3 order boundary condition. How the solution will look like? In fact, over the years, starting from 1929, I have given just a brief overview that how the expansion, how this velocity potential can be expanded. And it is very clear that these problems are not Sturm Liouville in nature because the boundary condition is of higher order than the governing equation. We are dealing with a second order equation where the boundary condition is higher order. So in that, so what we did first time, I proposed this expansion formulae, which was earlier basically the expansion formulae. The difficulty was the orthogonal relation, basically orthogonality of the eigenfunction. Because of the non-Sturm Liouville nature, the eigenfunctions were not orthogonal, which was claimed earlier in various manuscripts, including JFM and Annual Review of Fluid Mechanics and Proceeding Royal Society of London. And so here I propose this after 6, you see orthogonal relation. What we call this as a orthogonal mode coupling relation, and this was made it orthogonal, and in the process the problem was solved. Analytically, the problem could be handled. Then recently, 2017, again we say that we talked about the convergence of such a solution, and we introduced the distribution function in the spectral representation. We presented the eigenfunctions, vertical eigenfunctions, and we gave the corresponding spectral distribution. And using the spectral distribution approach, we could show that yes, this solution converges. And here I just cite one case of finite depth here, and even if in the case of infinite depth, the expansion is this, and then the corresponding distribution of the eigenfunctions are given here, and then finally even if in the case of infinite depth, the series converges, the integral converges. Similarly, we went from 2-dimensional to 3-dimensional problem. It's become a little more, instead of a single series, we have 2 series. Here also we have given the expansion formulae, and then we generalize this result to, and various characteristics of these eigenfunctions we have mentioned here. And I believe the more general orthogonal relation is given from 2 to 3-dimensional here. Now then, we generalize this problem to 3-dimension in detail. Here the total expansion in case of infinite depth is given, corresponding orthogonal relations are given. And this is the expansion formulae. These are some of the kernel M satisfy various, you can see the delta function is coming into picture because, and so with this, this is a brief overview about in a homogeneous fluid in 2-dimension and 3-dimension. The same thing if you will go for a 2-layer fluid, we assume here that 2 layers, they have a common interface, and on the surface I have either the plate is floating, whereas at the interface we have the fluid in two fluid of different density there. That is the common interface of the 2 fluid. So in that case, the problem again, because apart from the pre-surface condition, I have the interface 2 more conditions are coming because of the kinematic and dynamic concern, and that makes the problem more complex. And this is very important. And again, the theory is well developed for this kind of the generalized the expansion formula for this class of problem. So now here I just give the formulas for the in case of 2-layer. We started with a 2008 in wave motion. Then we generalized this both in finite and infinite depth. The orthogonal relation was further generalized from single layer to 2-layer. Additional terms have been added here. and see this is additional term. S is the ratio because of the ratio. And then we go for the finite depth result. Then again we have the orthogonal relation for finite depth. Some of the eigenfunction characteristics I mentioned. Then we also talked about the characteristics of the eigensystem, basically the convergence of the solution, the vertical eigenfunction psi n, and we talked about the convergence of the solution in terms of Dirac delta representation we gave it of the vertical eigenfunction, and followed by, and beyond this you can have two more roots, and only there are, because we have two layers, so three positive. In fact, in deep water solution, if you look at, there is one root on the surface, then one root at the interface, first interface, then second root at the second interface, and it has infinitely many events in mode, which are local effect, what we call. Anyway, this is, and then corresponding expansion formula is given, and this is the corresponding orthogonal relations. With this, I will just briefly highlight the key points what we have discussed. The boundary value problem discussed here is they are not of Sturm Liouville in nature. The occurrence of higher order boundary condition and the structural boundary, including the edges of the structure. Various expansion formulae are derived for flexural gravity waves for in different cases. Here we have assumed that in all the cases, the roots of the dispersion relation, that means all the eigenvalues are distinct in nature, and they do not satisfy the classical orthogonal relation, and that was which was the problem, and we have generalized in each cases a different orthogonal mode coupling relation to make them orthogonal. Anyway, so some of the questions for the future. Whether there exists there can exist more than one progress wave. That means whether this dispersion relation will possesses non-distinct roots, and if the root they will collide, if mode swapping will occur, what will happen in such situation? How the solution? So basically, it leads to a multiple eigenvalue problem, and this is very interesting problem, and which is my next part of the talk for in 10 minutes. So this leads to the blocking dynamics of flexural gravity waves. And here, I just, without going to detail, I just say what happened. I just look at the dispersion relation. The dispersion relation is you can see it as a component tan hyperbolic term. Basically, the plate covered, most simplest plate covered dispersion relation in finite water depth. And you see this part, it's a polynomial of degree 5 multiplied by a tan hyperbolic function. If you look at the solution of this, what happened? And in deep water, tan hyperbolic kh will tend to 1, and this will be more simpler. It is a 5th degree polynomial equation. And in case of shallow water, when kh is much less than 1, it will be 6th degree polynomial. So in this, what happened here? And if you look at, if I just plot the curve omega versus k, in fact, it is interesting. For different values, we can see that at this point A, you have d omega by dk will be here. What will happen? In point, it's a point of inflection. Whereas B, the point B, and here you see P, these are maxima and minima. The maxima and minimum means d omega by dk will be 0. When d omega by dk is 0, d omega by dk in wave terminology, we call this as group velocity. Omega by k is called the phase velocity, whereas d omega by dk is called group velocity. So when the group velocity vanishes, here, when the group velocity vanishes, that means no energy propagation takes place. And this is what we observe, that there is a wave which exists, but there is no energy propagation takes place. This is a very unique phenomena which was reported recently we reported this in 2018 and analyzed what happened in such situation, how the solution, and also at the point A, you can see that, as I say, that there are two roots will collide there. Two of the roots will collide. So there are two roots collision takes place. There are maxima and minima which occurs, and in between, suppose I draw a line here, you can see between this maxima and minima, the maxima and minima where d omega by dk is 0 are known as the blocking point where energy propagation ceases. And between this, if I take any frequency, I draw a line, you will see that three roots occurring, and all the three roots are positive. On the left side, three roots, right side, three roots are occurring. That means three positive propagating modes are possible. And that means within the primary and secondary blocking B and P, there can be three propagating modes possible. All the previous study, what I have highlighted in the beginning, till this issue was not assumed. All the problems on wave propagation on flexural gravity waves were considered assuming that there is only one propagating mode, that is the flexural gravity wave. But here I am coming to a point where I am showing that the existence of three propagating modes. And also here I have not brought the slide here, but we can show that there are certain condition under which that d omega by dk can be less than 0. That means energy propagation will be negative, energy will be negative, and which does not exist in the classical sense. In fact, this concept was defined in the context of a black hole theory in quantum mechanics. And that I'm not going to that, but that's why this is sometimes we call this paper title was it's an analog of blocking dynamics. It's analogous to what we have discussed in the gravity waves, and also earlier it was discussed in the. It's an analog to the what has been observed in case of the quantum mechanics and in the black hole theory. So this is I'll just show again the root behavior. You can see distinct root, then you have double roots. There can be two root colliding. There are situations I have shown that 3 positive plus minus 3 positive roots are there. And here in this situation, you have negative energy propagation can take place. And then we have d omega by dk, that is again, and these are the roots. Now I'm showing how the roots are behaving above the blocking and below the blocking point. There is a single root here on the positive side. If it is no blocking, but then we are below the blocking point. But on the second figure, you see that it is just touching. There are two roots are colliding here. Here, two roots will collide, and here you have three roots. You are able to see three roots here. Similarly, and this is one of the recent study on which this was published just last month in the Journal of Fluid Mechanics. The volume issue has come now. And then you have various cases we have taken how the roots movement is taking place when you change the frequency. So I'm not going to the detail of this problem, but here, what happened here, when I just say that in the single propagating mode, you have radiation condition was very simple. It was one wave which was incident, one wave that was reflected in one incident wave, one reflected wave, one transmitted wave when a structure you place. But in the other hand, when you have a multiple propagating modes, you have to take all these modes, because you have maybe one of the wave is incident wave, but it will lead to three different, or I just took it P, but in our case we have seen here that three propagating modes are existing. If this is the reflected wave, what will happen to the other modes? How they behave, whether one will be incident, which direction they will propagate. These are some of the issues which has been addressed in this paper of the JFM, Journal of Fluid Mechanics recently. And then coming back to the expansion formulae, the expansion formulae initially was given in the case of a distinct root, and that was in case of infinite. I just briefly mention here. And but in case of when there are two roots, double roots will occur, then in that case, this dispersion relation, expansion formula will be further generalized. This is an unpublished work now. We are working on this. But in case of treble root, then again this formula is further generalized, because what happened in case of a single root, our this h double dash k will not be zero. It is assumed distinct to all the solutions what we have earlier given. Their h double dash k is not equal to 0. Here h double dash k is 0. H dash k will be 0. So because of h dash k is 0, h double dash k is coming here. But in the case of three roots, you will see that h double dash k will be 0. So that means the solution has to be given in terms of h double dash. And this has been all the solution has been obtained by using, as you all know, that the Quasi-residue theorem, when you have the poles are not distinct, multiplicity p, that concept has been borrowed and to get the solution here. It was very conceptual. It's a very good concept that how to utilize this to obtain the solution of a partial differential equation, and that was very interesting. Similarly, in case of finite f, the solutions are obtained, and this is the solution in case of single root, which was earlier known. Double root and triple root, this is given here. Now, that is in case of homogeneous fluid. Now, coming back to a two-layer fluid, what we did, we also looked at the solution here, how the two-layer fluid works. In case of two-layer fluid, you can see if you plot the omega, the frequency curve, frequency versus the wave number curve, I see in the surface mode, we have two modes because of two-layer. On the surface mode, we have the flexural. This graph, you can see that there are three roots. Blocking can occur either of the mode, either in the surface mode for a single frequency, or into the for a in between point, you can see that the k is 0. And that is the point where the buckling will occur. The k is non-zero, but then you are able to see that the frequency is 0. That means no wave is propagating there. So that is the situation when the structure buckle. There are two issues here we consider. One is buckling, one is blocking. Blocking is the point the energy propagation ceases to occur, as a buckling the point where the wave velocity will be vanishing. Basically, velocity ceases. So now coming back to this picture here, it's more interesting. Here you see that under that at a point for a particular frequency, you can see that both surface and internal mode, there are 1, 2, 3, 4. In each cases, you will see that the line I have drawn, you will see 4 roots are occurring. That means 4 roots are occurring in this case. So that means earlier in single layer fluid, I have 3 roots occurrence for a single frequency. Here for a single frequency, you can have 4 roots also. So that means I can have all possibility, single, double. In case of 2 layer, there can be 2 roots. One is in the surface, one at the interface, which was our earlier study. Then we can have wave blocking occurs where the roots will mode swapping will occur. So the roots, double root will occur, and even if point of inflection, saddle point will, all these issues will come. And then we are having situation where the 4 roots also is possible that propagating 4 propagating modes. The idea is that when 4 propagating modes are there, we need to know which wave is propagating in the positive direction, which wave is propagating in the negative direction, and how each of these waves interact with each other, and what is the combined effect. In fact, some of these issues have been addressed in case of surface wave, that is the phenomena Bragg scattering, and that concept now we are working on the triad. We are here also in the case of 2 layer, 3 modes are colliding, or 3 wave modes are interacting, and triad resonance. And when here also in 2 layer, we have 4 modes are interacting, and the concept of dead water analog also is established here. And I'm not going, my time is almost coming to an end. So with this, again, we generalize this problem to both floating and a submerged plate. Here also you could see the existence of this kind of blocking dynamics, blocking phenomena. And with this brief introduction about blocking, I will come to almost come to an end. And here what I mean to say that the solution, the multiple eigenvalue problem, these problems are multiple eigenvalue problem where the roots are not distinct. They make mode swapping may occur. The roots may collide with each other. In such situation, how the physical situation is handled, how the solutions are obtained, and how the different modes when the different wave mode when they collide or when they interact with each other, the physics becomes more complicated. We started with an engineering problem, did a lot of mathematical juggleries, and then at the end of the day, we need to give a fruitful solution and physically explain what exactly is happening, and then we can convince the community that yes, whatever we are doing is quite useful. Anyway, so with this, I'll try to complete my talk. And some of the future scope, as I have already mentioned, that we have derived various results on blocking dynamics in both single and 2 layer fluid, but we are yet to analyze specific physical problem. We have only started a physical problem, that is in case of homogeneous fluid. We are going for submerged. We are going to work on the submerged plate problem, or the floating 2 layer fluid problems, and both the blocking dynamics and buckling, and then the bottom flexibility I have not taken, bottom rigid, bottom, all these problems all of them who all have contributed to for me to able to stand in front of you and speak about their work. And I express my thanks and gratitude to all my fellows, my mentors, collaborators, and guide. Thank you. And these are some of my group members at the moment. And now I have 7 students and 1 RA. They're working with me at the moment. With this, I'll conclude my talk. Thank you. Thank you for listening to me. Thanks once again.
Thank you, sir, so much. Now it's an open question to audience. If there are any questions from audience side. Hello. So anyhow, thank you, sir, so much.
Can I ask some question?
Yes, sir. Yes, sir. You can.
Yeah, it's very interesting observation. So actually, what could you have proposed that these are a lot of work, lot of things to understand. Definitely, kind of negative energy or negative wave energy. You have first time you have found it. What could be the reason? Which was before the surface waves, the dispersion relation, and now you found the other 3
See,
mode of.
I'm coming to the point. Basically, it was a. See, there are 2 issues. In case of plane wave propagation, such issue will not be there. Basically, when the forces, the compressive forces or the axial forces will be very high, it is because of the axial force. For a certain limit of axial force, in fact, for last 20, 30 years up to 2000, in fact, I have my past student also work taking the compression effect. When we added the compression, one of the issues I'm talking about, when the compression effect on a floating plate is taken, what happened after? For small compressive force, nothing happened. But when the compressive force becomes high, the structural bending starts. And that bending creates the problem. One of the issues is the bending of the structure. When high compressive force is there, high tensile forces are working on it. That is physically one of the viable conditions. Because basically this is a concept which has been well studied in case of a structural, basically bridge collapsing and building collapsing.